To the lecture on Biological Chemistry Foundations. This is a review lecture that focuses on the chemistry and organic chemistry that is necessary for biochemistry, and it's pitched at a level that will help with the MCAT review. Now, it certainly doesn't cover all the chemistry or all the organic chemistry that's needed for MCAT, but wherever possible, I've tried to broaden the focus out a little bit to be more generalized to help at least cover some of the topics I think will be helpful. It's a little bit longer of a lecture. I like to do 25 to 30 slides per hour. Here I've got about 40 slides, and there's a whole lot of lecture objectives because I wanted to hit all the points that I think are important along the way, and this could be used kind of as a reference. So you see there's 2 pages of lecture objectives, but each one is fairly focused, and that will help. Okay, let's get started. So we're thinking about biochemistry, which is the chemistry of life, and that is organic chemistry. And organic chemistry, of course, is the chemistry of carbon. And when we think about organic chemistry, we are most likely going to see carbon, hydrogen, oxygen, and nitrogen as the most prevalent elements that we'll see. But there are others. We'll see sulfur and phosphorus. We'll see inorganic ions. We'll see magnesiums and seleniums, all kinds of stuff. So this is just the main. And we're going to get into the idea about organic chemistry and covalent bonds. Now, for inorganic chemistry, a lot of times you're looking at covalent bonds, but also non-covalent bonds. But for organic chemistry, really, we're looking at covalent bonds. And a covalent bond is when two atoms come together. And you'll remember the octet rule says that for any atom, it wants to have 8 electrons in its valence shell. The valence shell is the outer shell of electrons. There's supposed to be 8 electrons out there. And if you look at chlorine, we'll see in a moment on the next slide, but chlorine has 7 electrons in its valence shell. And it says if I could get one more electron, I could have 8 electrons. So two chlorine ions can come together and they can form a chloride, atomic chlorine here, which is 2 electrons being shared. Now these electrons are being shared, meaning they spend time over both of the nuclei. So you have 8 electrons and you have 8 electrons, and that sharing is called a bond. Now, that's true for fluorine and bromine, all the halogens, because they're in the 7 group, and we'll see that in just a moment. Carbon has 4 electrons in its valence shell, and because of that, if it's going to get 8 electrons, it's going to need to form 1, 2, 3, 4 covalent bonds to share 4 electrons. Hydrogen, well, hydrogen simply, it's the first element. It has only 1 electron. There's only a 1s orbital. And at most, it can have 2 electrons in that 1s orbital. So it follows what's called the duet rule, 1 or 2 electrons. So it's a little bit unusual. But hydrogen, because of 1 electron, 1 proton, is going to form 1 bond. Oxygen is in group 6. And so it has 6 valence electrons. So it wants to form 2 covalent bonds to get 2 shared electrons. Nitrogen wants 3, but it can also do 4. That's a special property we'll see in a little bit. Sulfur is very similar to oxygen and phosphorus. So when we think about this, 4 bonds, 1 bond, 2 bonds, 3 bonds, it's what you very commonly see. It's what you very know. But why is that? What is it about the periodic chart that tells you these things? So if you look at the periodic chart, you have the idea of valence. And valence is how many electrons are in that outer shell. And if you look, there are columns here and there are rows. And we're going to be talking about the columns because they're numbered 1A, 2A. You jump over here, you see 3A, 4A, 5A, 6, and 7A. You may have to blow this up to see it. And that tells you how many electrons are in that outer shell. Of course, hydrogen's unusual and has a 1s shell, so there's only 2 maximum on the outside. Of course, these are very similar here as well in the 2 group here. But once you get over to the right side, where you have group 3, 4, 5, and 6. Well, okay, so oxygen is in the group 6. It wants 8 electrons. 8 minus 6 is 2. It's going to need 2 or 2 bonds. Nitrogen is in the 5 group and carbon in the 4 group. And so you can see how I'm getting those valence numbers from. And it's described over here on the right. Now, of course, the transition metals are a little bit weird because they have D and F orbitals and all those kinds of stuff. So let's just keep it simple and look at the groups here. Now, we'll also be talking about electronegativity, and electronegativity says how likely is a nucleus to hold on to its electrons. And if you remember, electronegativity increases as you move down the chart. Electronegativity increases as you move to the right, because as you move down and to the right, the nuclei are getting bigger, and that larger amount of positive charge will have a stronger drawing effect on those electrons than will the smaller nuclear sizes. And that's kind of important. In the previous ladder coming up, you'll see how well these atoms will hold on to their electrons. Okay, when we think about carbon-carbon bonds, this is true for carbon and oxygen, carbon and nitrogen. When we think about the covalent bonds, one thing about organic chemistry is you can form a single bond, which is sharing one pair of electrons. You can form a double bond, two pairs, or a triple bond, three pairs of electrons. Now, double bonds are common for nitrogen and oxygen, way more common for oxygen than nitrogen, but you do see it sometimes. Triple bonds really are only going to be seen in carbon compounds, carbon-carbon bonds, although the molecule cyanide has a carbon triple bonded to a nitrogen. So much more common to see single bonds, but double bonds, but carbon can see any of these. So when you see a single bond, that means one set of electrons are being shared. If you look at the two carbons here, that bond that's connected them says those are two electrons that are being shared. Here, the covalent bond between the carbon and the hydrogen atom, two electrons are being shared. And then you don't know what's on these other sides over here. But if you count, there's two electrons, 4, 6, and 8. So that carbon is happy. 2, 4, 6, and 8, that carbon is happy because it's sharing one set of electrons. You can also have a carbon-carbon double bond here. What you'll notice right now is carbon wants to form 4 covalent bonds. And this picture is showing you there are only two other elements over here, 2, 4 electrons, but carbon says I want to have 8. And so the partner carbon atom over here says, well, I can help you out. I can share two sets of electrons, so 2, 4, 6, and 8. 2, 4, 6, and 8, that's the double bond. And it's oftentimes represented by two lines there. And of course, the triple bond, 2, 4, 6 electrons are being shared, and then another element over here being added with 2 electrons being shared. So I know that's dull and boring. You know this stuff already, but it's important to go through that because we're going to see changes in bonds. Single bonds are going to become double bonds, or single bonded oxygens become double bonded oxygens. And it's very important to understand what that means in terms of what the electrons are doing. Now, there is a configuration where you can have a double bond beside a single bond. That's fine. As long as carbon has 4 bonds, it's all right. You can see the single bond, single line, double lines there. And don't worry so much about the fact that it's isopentyl. 1, 2, 3, 4, 5 is pent, and iso because it's branched. And the fact that it's a double single bond is a thing called conjugation, where two of these bonds are beside each other. Now, a conjugated system is where you have a double bond, double bond, single bond. So that's conjugation if you have more than one set of double bonds there. But when you close this ring, in this case, this is a benzene ring, 6 carbons and an alternating double and single bond, you actually set up what's called an aromatic group, where the 2p pi orbitals will have delocalization of electrons over the whole network here. So in this case, it's aromatic. And the 6 carbon is a benzene ring, and of course you can put substituents on there. So the names are, if you think about the bonds, alkane, A and E means a single bond, E and E, alkene means a double bond, and alkyne means a triple bond. And if you have a methyl group, there is methyl. If you have a CH2, it's methylene. If you have a CH, it's methenol. And the same idea, the Y and the Y and the E and the E and the A and the A, although the A is not really shown out so much here. So the methyl group says carbon has 4 things on it. It's getting 4 single bonds. Here, the methylene group says, well, there are 2 hydrogens and there's 2 other things. The methanol says there's only 1 hydrogen on there. Other things I think MCAT wants you to know is that a CH3 group is called methyl, 2 carbons is ethyl, 3 is propyl, 4 is butyl, 5 is pentyl, and you can go all the way up. If you have a single line here, it's the propyl. But if you have a branch, it's the iso, in this case, isopropyl because of 4. So over here you saw this is an iso group as well. So a little bit more detail, but nomenclature is very important. If you don't remember, this is a great place to go for that. So continuing on now, these are the functional groups that we'll see. These are all organic functional groups, but we'll see these in the biochemistry and all the stuff we're going to do. So you really must have a visual understanding of what these things are by name and really by structure. It will serve you well on the MCAT. It will serve you well in this program. So an alcohol is going to be a carbon that's bound single bond to an oxygen. Oxygen likes to have two bonds. So it has two bonds with the hydrogen and then of course the carbon. An aldehyde is going to have a carbon that's double bonded to the oxygen. So carbon has four bonds. We don't know it's an R group over here, but an aldehyde specifically has one hydrogen attached to what's called a carbonyl. The carbonyl is a C double bonded O. A ketone has R groups on either side of the carbonyl. Aldehyde has one R group and one hydrogen. And then a carboxylic acid will have a carbonyl with an additional single bonded oxygen. So C double bond O with an OH. You absolutely must know alcohol, aldehyde, ketone, and carboxylic acid. Now you can go a little bit further here and come up with an ether linkage. An ether is where you have an oxygen bridging two carbons. Okay. The difference is before we had an alcohol that had a carbon, oxygen, hydrogen, an ether is a carbon, oxygen, carbon. And then if you put carbonyls on either one of these carbons here, then you have what's called an acid anhydride because it should be a carboxylic acid. You've just attached two of those things together and there it is. So sulfur and oxygen are very similar. They're in the same group, in the same column. So sulfur likes to have two bonds as well. So if you see an SH and you think about OH, that's right. Alcohol, thiol. Thiol is the name for the sulfur. So it's called a sulfhydryl group or a disulfide. Two sulfurs are bound together here. We're going to talk about the electronic properties pretty soon. Now you can bring in a amine group. Remember, nitrogen likes to have three bonds. So there's two with the hydrogen atom, one with the carbon here. So that's called a primary amine. There's one R group off on that side. There's a naming coming up here in just a moment. This is a quaternary amine. There are four R groups on this nitrogen. Remember, nitrogen normally will form three bonds, but sometimes it can do four bonds. And when it does four bonds, it's sharing a pair of electrons that normally aren't shared. And so you see a positive charge. We'll discuss that coming up. So there's some special groups down here. There is an ester group. If you have a carboxylic acid and you remove the hydrogen atom and put in its place an R group, that is an ester. And then a thioester is the same thing, but instead of an oxygen, you have the thio, which is the sulfur, so a thioester. You can have a phosphoester where instead of a carbon double bond, you have a phosphate. Now, phosphorus is different. It's in a different group, so it has to have a different number of bonds. So it has a different configuration, but there you have that. And then an amide linkage. An amide is where you have the oxygen is replaced with a nitrogen. Normally you'd have a carboxylic acid. If you remove the OH and put an NH, that's an amide. Now you may know this from proteins. Whenever you have two amino acids, they are hooked together with a carboxylic acid and an amine group, and that's called a peptide bond because the peptide is a unique structure for proteins, but it's an amide bond is what it is. So one thing that we'll talk about in the next lecture coming up is that these groups, carboxylic acid, amine group, phosphate groups, are ionizable, which means the oxygen atom will hold on to the electrons so much that the proton can come off. And the oxygens here will hold on to their electrons so the protons can come off. And the same thing for sulfate. And so you'll never see a carboxylic acid in a protonated state at pH 7. We will discuss this in detail, I promise. So carboxyl groups are going to be charged, and so they're called carboxylate to let you know they're negatively charged. Phosphate, sulfate, the 8 lets you know that it's negatively charged. Now the same thing is true. Amine groups are basic, and by basic it means they like to pick up an extra proton. And at physiological pH 7.4, 7.2, these things will be protonated. And so nitrogen with three bonds will be neutral, but nitrogen with four bonds will be positively charged. And so we see a primary amine, there's one R group. Here's a quaternary amine, four R groups. So if you have two R groups, there's primary, secondary is two, tertiary is three, quaternary is four. So these are going to be charged at the pH, at the body pH. And what that gives rise to is a thing that we call ionic interaction. And ionic interactions means a interaction, a dipolar or charge interaction between formal charged molecules here. What you'll notice over here is you see there are phosphate groups, and because of the phosphate and the oxygens, they are deprotonated, and because they're deprotonated, they have a negative charge, and that negative charge is just sitting out there. Water loves negative charges. But if a magnesium ion comes along, it has a 2 plus charge. That formal means a permanent charge, is going to be attracted to these negative charges and they're going to come together. It's not a covalent bond, it's not a permanent bond, it's an electrostatic interaction. It's like two ends of a magnet come together or opposite charges coming together. And here for a protein, you'll see here's a carboxyl group, carboxylate because it's negative charge, and this is a primary amine, it's got a positive charge. And so those red dots are showing you that these are electrostatically attracted to each other, not a covalent bond, but an electrostatic interaction. And there's another one down here between a carboxylate and amine group going the other direction. And what these things do is it allows the magnesium to stick onto this phosphate. It allows these two, the amine group and the carboxylate group, to stick onto each other. And it allows you to have some structure here in this little loop of the protein, or structure to the molecule up at the top. And this is true too for DNA. We'll talk about these bonds coming up. But here for DNA that will bind to a specific protein, you'll have an amine group coming off of the protein, and you've got a phosphate on the DNA, phosphate negatively charged, the amine group is positively charged, and so they set up that ionic interaction. These are called weak interactions because by themselves they have almost no energy. It's tiny, it's negligible. But there are so many ionic interactions within a protein or protein DNA or molecules or whatever that it adds up to quite a bit of energy. And we'll develop that idea a little bit better later. So that the idea that you have charged groups, they can form ionic interactions, and we'll talk about those coming up. Okay, let's talk more about the polarity about bonds. So if you remember, there is electronegativity. I mentioned that before. And electronegativity says you get more electronegativity as you move down the periodic chart. You get more electronegativity as you move to the right. So hydrogen at the top left of the periodic chart has the smallest amount of electronegativity there is. And chlorine, being on the far right of the periodic chart, has some of the greatest electronegativity there is. So when the hydrogen and the chlorine come together and they form this bond, hydrogen has 1 electron, chlorine has 7. And so by coming together to make hydrogen chloride, then they will share those 2 electrons, and both the hydrogen and the chlorine will be happy. But what you'll notice is because the chlorine has so much electronegativity, it's going to draw the electrons over. The electrons will spend far more time on the chlorine than on the hydrogen, and that gives the chlorine a partial negative charge. That gives the hydrogen a partial positive charge. This is a critically important concept for biochemistry and for reactivity. Now, we don't see hydrogen chloride that much, but what we do see is we do see carbon-oxygen bonds and carbon-nitrogen and carbon-sulfur here. Carbon is a little bit to the left, oxygen is a little bit to the right. Oxygen has greater electronegativity, carbon has less electronegativity. For a carbon-oxygen bond here, the electrons will spend more time on the oxygen atom and less time on the carbon, so there's a delta negative for the oxygen and a delta positive for the carbon. And that's going to be important for some of the organic reactions that we're going to see. Same thing for nitrogen. Nitrogen is going to draw the electrons. Sulfur will draw the electrons. So in each case here, the carbon is going to be delta positive. If you think about a real molecule, here is an AMP molecule. We'll talk about that later. And over here is going to be a fatty acid. We'll talk about that later. But because of the electron withdrawing properties of that double bonded oxygen, of course, there's phosphorus and oxygen over here, the electrons will spend more time on the oxygen up here, less time on the carbon, so you have a delta positive. And if a nucleophile, a nucleus, electron-rich species comes, it can react with that delta positive. That's why that little arrow is showing you that. Okay. So if you have 2 atoms that share the exact same electronegativity, like these 2 chlorine atoms will come together to form a diatomic chlorine molecule here, then there is no winner here. The electrons will spend an equal amount of time on each of those chlorines, and we say that the bond is completely equally shared. There's no polarity there. When we look at the periodic table as a whole, we can see these trends overall. Electronegativity increases as we move to the right on the periodic table, and electronegativity will increase as we move upward on the periodic table. And when these two are brought together, we see that fluorine should be, and it actually is, the most electronegative element. Of course, chlorine is as well. The group sevens in general are going to be the most electronegativity. But from before, we mentioned that carbon was more to the left and oxygen was more to the right. That's why carbon is less electronegative and oxygen is more electronegative. You can see these trends when you line up the elements. Now, an MCAT question may be, why are the noble gases not included in this electronegativity discussion? If you recall, the group 8 elements have a full complement of electrons. And because of that, they don't have any open spaces for an electron, so there is no driving force for them to acquire electrons. They don't seek electrons. And so the group 8 elements are left out of the electronegativity discussion. That's why it ends here with the group 7 elements. Okay, so this idea of a polar bond is going to be important for the thing we call hydrogen bonds. And a hydrogen bond sounds like a real covalent bond, but it's not. It's not a covalent bond at all. See right there, not a covalent bond. But instead, if you have a water molecule where the hydrogen is attached to an oxygen, and over here you have an oxygen and a carbon, the oxygen is more electronegative. It's going to pull electrons towards the oxygen, give it a delta negative. Over here, because of the oxygen and the water, it's going to pull the electrons toward the oxygen, giving that hydrogen a delta positive. Now that's going to set up what we call a dipolar interaction. These two atoms will be attracted to each other because of the opposite partial charges. And they're going to face each other like two magnets of opposite poles here. And that attraction will allow these things to be a hydrogen bond. Now, it's not permanent. It's not shared electrons. These things can be broken pretty easy. It's a very weak interaction. But if you look at biological molecules, there's thousands and thousands of these, and all that energy adds up together. So down here below, again, the same thing is true. The nitrogen has a little bit more electronegativity. It's going to pull electrons into itself. Again, the hydrogen is going to be electropositive, and so these things will be attracted. And you can go down and see all these scenarios. Here's a carboxyl group. So that proton now is going to be very unshielded. It's going to have a delta positive, and so it's going to be seeking. Now, in this case, we're going to talk about deprotonation coming up in a moment. But the same thing is true for an alcohol, for an amine. These hydrogens are going to be delta positive because they're attached to an electronegative atom. And then over here, of course, we have an electronegative atom. That's going to be the delta negative. That's going to set up the negative side here. So fairly important concept. So we've seen ionic interactions that are between formal charges. Hydrogen bonds are between partial charges, and it must be a hydrogen attached to an electronegative atom and then an electronegative atom as the negative donor. And of course, if you have a polar bond where you have delta negatives and delta positives, because water has delta positives and delta negatives, the more polar the material is, the more water soluble it's going to be. So if you think about down here, this is a carbohydrate molecule, and because of all these oxygens that are electronegative, that's going to make these oxygens have a little bit more of a delta negative, and the hydrogens are going to have a delta positive. And because of the water, these carbohydrates are going to be very soluble in the water. Very important concept. So if you think about it, let's look at the solvent properties of water, because water, we're aqueous beings, water's all around us, it's always there. So we'll see that the water molecules have their delta negative and their delta positive. So if you have a salt like sodium chloride, where you have a formal negative and a formal positive, well, of course, salt dissolves in water because the positive sodium and the negative chlorine can make really nice electrostatic interactions with the water. But let's think about something that's not polar, non-polar. Think about oil or fat, if you would. There's no polarity in those bonds. There's no charges in that bond. Water just doesn't know what to do with it. Water tries to dissolve the oil, but it just does not find anything that it can work with. And if you know anything about oil and water, if you were to mix these two things up like a bottle of salad dressing, like oil and vinegar, the water will settle on one phase and the oil will settle on the other. Why do these things separate out? Sodium chloride and water love each other. The sodium and the chloride dissolve, you have a dissolved solution. But here, the hydrophobic, the oil and the water separate. Well, it's pretty easy to look at that. When the water comes, the water molecule itself is very polar and it wants to have polar interactions. It wants to have hydrogen bond interactions. But the nonpolar molecule says, well, I can't do that. I don't have anything for you to look at. So the water says, well, what I will do is I will form a cage around the molecule and I will form my own polar network here so that all the bulk water on the outside can form hydrogen bond interactions with the water. You sequester the molecule with a cage around it, and that's fine. You sort of get the gist here. When you mix those two things together, you see smaller and smaller and smaller drops that the water is trying to solvate here. But what happens is the water has to organize itself to solvate each of those individual molecules. Now, this is a single molecule, and down here you have 100 kabillion zillion molecules. And the water says, you know what? It's a lot of work and it takes a lot of energy for me to form cages around every single molecule. So what I would rather do is I would rather let the oil separate where it can interact with itself, let the water separate where it can interact with itself, and I will have only one contact interaction here. So at that point of contact between the oil and water, only a few water molecules have to organize themselves to make that cage or that water cage that's present there. And that allows you to use the least amount of energy for these two. So if you were to shake that oil up, you have a ton of water organized around a ton of organic molecules here, but if you give it time to settle, it'll dissolve, separate out into these two different phases. And so that's going to be a secret of life. And the secret of life for membrane formation, we know that there are hydrophobic parts of a bilayer. There are hydrophilic, which means water loving. And so the water loving will face outward towards the water, and the hydrophilic, the hydrophobic, the stuff that's not polar, will face the inside. And of course, we know that there are proteins that have hydrophobic parts that can be inside the membrane. Proteins have hydrophilic parts that can be outside the membrane, and so forth. And so even when it comes to a protein itself, we'll talk all about protein structure and function coming up, but there's going to be parts of this protein that are polar and are very happy to face outward. There's going to be parts of the protein that are hydrophobic that will fold into the deep interior where they're protected from water. So the parts that like water are on the outside, the parts that don't like water are very deep inside. And so the hydrophilic and hydrophobic interactions is what drives a lot of the structural details of the molecules we're going to be talking about here. So hydrophobic interactions is another weak interaction. It is the driving force that makes non-polar molecules sequester, as you saw in the previous slide. So we have ionic interactions, we have hydrogen bonds, we have hydrophobic interactions, and pretty soon we're going to see van der Waals coming up here in just a moment. But we haven't talked about those yet. The other thing we know is that the bond polarity is going to affect reactivity. And the reactivity says, well, of all these atoms that are present here, where is the most likely site of a reaction going to take place? Well, reactions tend to take place where we have active atoms. And active atoms mean partial charges or formal charges. You can have a nucleophilic attack or an electrophilic attack. That'll be covered a little bit coming up here. And so if you have a CH2, that's not very reactive, but if you have a delta positive, if there's another molecule that has a delta negative, the sulfur with its unpaired electrons will be attracted to this delta positive. You can see the sulfur attacking that carbon and forming a new bond. You see that bond right there? That's a nucleophilic attack. And then you have this bond is going to break. It's no longer going to be there. It's called the leaving group. And the AMP leaves behind. We will discuss this reaction a couple times in lectures coming up. So don't memorize the details, but now understand the idea. And so that just sets up a really nice set of reactivity. If you have a formal negative, like if this were an S minus with a formal charge, that would be a much stronger nucleophile. Or sometimes you can see water with a partial negative on the oxygen can be a nucleophile. Or you can see an OH ion. OH ion has a negative charge on it. It's a very strong nucleophile. So when you think about that, there are some very common reactions that involve oxygen atoms and sulfur atoms and similar ones, nitrogen atoms. But right now, we're going to be looking at oxygens here. So you can take an acid, a carboxylic acid. You can take an alcohol, And that alcohol oxygen will serve as a nucleophile that will attack the delta positive carboxyl group, and it will form a new bond between the oxygen and the carbonyl, and that gives you an ester linkage here. What do you lose? Well, when that nucleophilic oxygen hits that carbon, it's going to knock that OH off, and the OH will pick up a proton and become water. So it's called the elimination of water. An H and an OH form water, and then the oxygen is the new bond. There's the ester. And you can do the same thing with a sulfhydryl group. You see this sulfur. Remember, sulfur and oxygen behave a lot alike. So the sulfur electrons can attack the carbonyl carbon. That knocks the water off, and you're left with a sulfur group, so a thioester. Amines can do the same thing. There are unpaired electrons on the amine that can attack the carbon. That will give you an amide linkage. And again, you lose the OH from the carboxylic acid and you lose the hydrogen atom, and that gives you the water. And phosphoric acid will do the same thing. You get a phosphoester because now the oxygen attacks the phosphorus nucleus there. If you take two acids and bring them together, if it's a carboxylic acid or a phosphorus acid, doesn't really matter. In this case, you're looking at two phosphorus atoms. You eliminate that water and you allow this oxygen to be the nucleophile that hits that phosphorus. You're left with a phosphoanhydride. It just says anhydride because you've lost the water here. Because it's phosphate, it's called a phosphoanhydride. If it's a two carbons, it's just called an anhydride as well. And you can have a phosphorus and a carbon, which is a carbon phosphorus anhydride. We'll see a couple of those coming up as well. So we can sort of back out a little bit now instead of saying, well, let's not just look at carbon-oxygen reactions or nitrogens or sulfurs. Let's look at the major reactions that we're going to have on in the biochemistry. There's going to be a group transfer where part of one molecule is pulled off and it's stuck onto another. So it's transferring a group, like you can move an amine group or an oxygen or something like that. It's a group transfer. A good example of that's going to be when you take a phosphate off an ATP molecule and you stick it onto another molecule, like glucose 6-phosphate. Cleavage is what it sounds like. To cleave is to split. So a cleavage reaction will split molecules into pieces. To condense means to join or to bring together. So that's two things that are separated become one molecule. They're condensed. A rearrangement is where you go from one isoform to another. So you can rearrange the atoms, like a citrate molecule can become an isocitrate molecule. They are isomers of each other, and the rearrangement is what lets that happen. Oxidation reduction, those are going to be when electrons are taken from a molecule or electrons are put into a molecule. Now you saw on a couple of earlier slides that when you see covalent bonds forming, that is not oxidation and not reduction. You're taking atoms that have electrons, and those electrons come together, they're shared. They're not added or removed from the system, they're shared within the system. For oxidation reduction, oxidation says you're taking electrons away. They're going somewhere else. And if you add an electron to something, you are reducing it as picking up an electron. So here are the examples like I mentioned before. Here's a glucose molecule. Here's an ATP molecule. You transfer a phosphate off of the ATP and stick it onto the glucose. There's the transfer of part of the reaction. We'll talk about this coming up with the glycolysis lecture about halfway through the course. A cleavage reaction is where you split a molecule. You see the phosphate is now attached. In this case, water comes in. It's a nucleophilic attack on the phosphate. And so the phosphorus comes off and you're left with the OH. You've now split that molecule. It's a cleavage reaction. When you want to bring two amino acids together, you've got a carboxyl group. Here is an amine group. They're two separate things. When they come together, you eliminate the water and form a new bond between the nitrogen and the carbon. That is going to be an amide linkage. You're condensing or bringing them together. And remember, when it's two amino acids, the fancy name is peptide. It's a peptide bond. And since there's two of them, it's a dipeptide. Three would be tripeptide and so forth. And then going on, here's a rearrangement. Glyceraldehyde 3-phosphate becomes a molecule dihydroxyacetone phosphate. We'll see these two molecules quite a bit when we do metabolism because they're two of the most important molecules that bridge carbohydrate metabolism with lipid metabolism and all kinds of stuff. And then oxidation reduction, what you'll see is this is a system that has two carbons that are together with single bonds. In fact, carbon has four single bonds. If you count the electrons, 1, 2, 3, 4, 5, 6, 7, 8, and there's 8, there's 1, 2, 3, 4. So together, if you go down here now and you do the oxidation, you see there is now a double bond. So carbon only has 1, 2, 3, 4 bonds apart from the double bond. Over here, it had 2, 4, 6 apart from the single bond. So you've lost 2 electrons. This doesn't show you where the electrons went. It went to a molecule called NADH that we'll talk about. But there are less electrons. So 2, 4, 6, 8, 10, 12, 14 electrons in that carbon system. But here you've got 2, 4, 6, 8, 10, 12. You've lost 2 net electrons. And the same thing is true here. Anytime you see a carbon with a single bonded oxygen and you see it become a carbon with a double bonded oxygen, it means you have lost 2 electrons. The carbon says, I have to share 2 sets of electrons in order to make my 8 and my valence shell. And that's shown a little bit better here. Here's the counting. So you see if there are single bonds, 2, 4, 6, 8, 10, 12, 14 electrons. If you share 2 sets, 2, 4, 6, 8, 10, 12, because you've lost electrons, you're now oxidized. And you can go the other way. If you add electrons into the right molecule, you can create the single bond and the 2 more electrons there. You are reducing going to the left, you're oxidizing going to the right. So let's see a real world example that we'll see quite a bit in the metabolism section. This is the molecule pyruvate, which is the last molecule of the pathway glycolysis. Over here is lactate, and lactate is going to be a reduced form of pyruvate. Now, wait. Hold on 1 second. Who says that this is reduced? Who says that this is oxidized? How in the world can you figure that out? Well, you can read the orange text over here and see it, but it's the same thing. There are 2, 4 electrons in those single bonds, and then 2, 4 are shared. So there's your 8 electrons, which you have 2, 4, 6, 8 electrons. Oh, okay. And then 10, 12, because oxygen has 2 on it. So that's where the 12 is coming from. But here you have 2, 4, 6, 8, 10, 12, 14 electrons. Remember, there's 2 unpaired electrons on the oxygen. You see there are more electrons in lactate. There are less electrons in pyruvate. So you say, okay, I can see that. But there's a rule of thumb up here. If you gain hydrogen atoms or if you lose oxygen atoms, that's going to make you reduced. If you lose hydrogen atoms or gain oxygen atoms, it means that you are oxidized here. Okay, so let's see. Wait a minute. So here is a carbon that has an oxygen. Here's a carbon that has, I don't see gaining or losing an oxygen there. But the trick is, if you have a double bonded oxygen, it's just like having a two oxygens instead of just 1. So this double bond says 2 oxygens, this single bond says 1. So you gain an oxygen going to the left. That means you're oxidizing going to the left. Notice over here on the right that you have a hydrogen. There's a hydrogen carbon single bond. On the left, that hydrogen carbon single bond is gone. And since you've lost a hydrogen now, you've gone from more reduced on the right to more oxidized on the left. And in fact, you lost a hydrogen over here as well. You've lost a proton that's missing on the left. So in general, gaining electrons or losing hydrogens means you're oxidized. Gaining hydrogens, losing oxygens means you are reduced. Now we'll see this time and time again. So we'll talk about lactate dehydrogenase and how it all works and so forth. And over here, just to let you know about the different forms, hydrogen atom has a hydrogen, 1 proton and 1 electron. So that's the intact atom. You can lose the proton, the electron can stay behind, and so a proton by itself is just called a proton, H+. But remember, hydrogen has a 1s electron shell, and that 1s shell can hold 2 electrons. So if the hydrogen atom picks up an extra electron, it will pick up a negative charge, and it's called a hydride. And in fact, when you lose this hydrogen atom here, you're not just losing 1 proton and 1 electron, you're losing 2 electrons here, and those 2 electrons are going as a hydride up here to the NADH. And That's why carbon says, wait a minute, I used to have two more electrons, but I just lost those two electrons, so I have to form a double bond with this oxygen to make up for the fact that I lost those two electrons. That's how you can reason your way through the oxidation and the reduction. Now for MCAT and for chemistry, you might be looking at copper 2 becoming copper 3 or iron 2 becoming iron 3, and that plus 2 or 3 tells you that you have more or less electrons based on what the number is. And so in that case, it's a little easier to see because the number, the plus or the minus, tells you what the charge is, and the charge is changing because of electrons. Okay, so the same thing can be true for sulfur. Remember, sulfur behaves like oxygen, and we'll see this quite a bit. We'll see this in protein structure, but we're also going to see this in metabolism. There is a thing called a sulfhydryl group. A sulfhydryl is like an alcohol, but instead of an oxygen, you have a sulfur. And there's two sulfurs can come together, and those two sulfurs can bind and form what's called a disulfide bond. You can connect these two molecules through that disulfide bond. And you see here you have an SH, there is a hydrogen on there. Here there is no hydrogen on there. So by the same token, there's only one cysteine, sorry, one sulfur here. There are two sulfurs here. So you have gained sulfur because you gained a bond, and you have lost hydrogen down here. So you must be going from a more reduced to a more oxidized, going from a sulfhydryl to a disulfide. That's going to be important later on in metabolism. But if you don't believe that, you can say, well, let's count the electrons. Here is a CH2SH. There's your CH2. There's your SH. The sulfur has 2, 4, 6, 8 electrons, 2, 4, 6, 8 electrons. There are 16 total electrons in this system. But when they come together and they bind, you have 1, 2, 3, 4, 5, 6, 7, 8. Wait, 10, 12, 14. So there's only 14 electrons in the disulfide bond, whereas there were 16 electrons in the two sulfhydryls. So again, the system overall has lost electrons, and so it has become oxidized. So two ways that you can see that. Okay, so the next thing we think about is if you're gaining electrons or if you're losing electrons, okay, that makes sense. Oxidation, reduction, that makes sense. But gaining oxygen or losing hydrogens, let's look at that again. We have carbon oxidation states. So carbon can have three hydrogens on there, and it's called a methyl group, and it could actually be methane, CH4. This is the most reduced form of carbon. It has all hydrogens on it. And if you change one of those hydrogens with an oxygen atom, you are losing a hydrogen, but you are gaining an oxygen. And that means you are oxidizing. So an alcohol now is going to be more oxidized than a methyl group. See that? And if you were to take electrons out of this system and you were to create a carbonyl, a C double bond, now you have two covalent bonds instead of just one. And because that's like having two oxygens, you have now picked up a second oxygen and yet lost another hydrogen. And so the aldehyde is more oxidized. And if you go to a ketone, you're losing a hydrogen. Okay, so it's harder. You're not picking up an oxygen because you still have a double bond there, but you're losing a hydrogen. The ketone is more oxidized than an aldehyde. And of course, a carboxylic acid, you're losing this group over here. You're adding an oxygen on. It's going to be more oxidized. And then if you lose the R group and the oxygen here, you have carbon with two double bonded oxygens. That's like having four oxygens bound to that carbon. Carbon dioxide is the highest oxidation state that there is. Okay? And you can also make the argument about electronegativity. Because the oxygen is more electronegative, it's going to pull the electrons up towards the oxygen. The carbon is going to be delta positive. If you have the R groups over here, carbon and the carbon, they're going to pull electrons a little bit more than the hydrogen does. And so this will be even a little bit more electropositive, the carbon, than the aldehyde group over there. So that's why it's a little bit more oxidized as well. So there's a couple ways to work your way through that. Okay, so if you remember for carbons, you see here there's a methyl group, here's a methylene group, And here is a methynyl group over here. A methynyl group is going to be the CH. It's right in front of my face, but it's okay. So methyl is the most reduced, methylene is more oxidized, and methynyl is going to be the most oxidized. We'll see this coming up as well. Okay, the last slide here on the really fundamental review of chemical bonds is going to be nomenclature. And nomenclature is much easier if you can talk about the nomenclature for whatever molecule you're looking at. So there's just some general rules that we'll talk about here, but all the nomenclature will be handled at a lecture specific place as we go through here. But the idea is for any one of these molecules, they're going to have pet names, glucose, okay, or linoleic acid, linolenic acid, whatever. They have these names, but there's an organic structure. And usually you start at the end of the molecule that has the most oxidized carbon. Now, if you start over here, it's pretty easy to see, well, okay, here's a carboxylic acid, and we know that's going to be like having 3 oxygens, so that's pretty oxidized. Over here is an OH, that's like 1 single bond, so that's 1 oxygen. I think the carboxylic group is going to be more oxidized, the alcohol is less. So obviously this is the most oxidized, and this is going to be carbon number 1. So you go from 1 to 2 to 3 to 4. And so that's where it comes from. And then we'll find naming. If there's a branch here, you can say at carbon number 1, 2, 3, there's a hydroxyl group here. 1, 2, 3, 4 carbons. So remember methyl, ethyl, propyl, butyl for 4. So this is a butyl group. So it is a 3 hydroxy butyl, but because of the carboxyl group out here is butyrate here. So 3 hydroxy butyrate there. Some organic texts will use the Greek nomenclature where you have the most oxidized carbon. The one closest to it is the alpha carbon, the beta, and the gamma carbon. So you could call this beta hydroxybutyrate, which is actually its more common name, beta hydroxybutyrate. We'll see this when we talk about ketosis and metabolism. Over here, we start with this molecule. What is the most oxidized? You look over here at the phosphate and you say, boy, look at all those oxygens. Whoa, this must be the most oxidized in the molecule. Well, that's not true. You're looking for the most oxidized carbon atom, the most oxidized carbon atom. Same here, you see a aldehyde with the C double bond O, but each one of these are single bonded oxygens, so they are not as oxidized as the aldehyde is. And here, of course, that's just a C double bond O. So obviously the aldehyde is going to be the most oxidized in carbon number 1, 2, 3, 4, 5, 6. And because there's a phosphate group on carbon number 6, we call this glucose 6-phosphate. Now, how did you know it was glucose and not fructose or galactose or xylose or what? We'll talk about that when we do the carbohydrate lecture here. One more time for fats. This will be pretty familiar for most of you, I'm sure. Again, the carboxylic acid, this is the only oxygen-bearing carbon, so this must be carbon number 1. And you simply go down chain 2, 3, 4, 5, 6, 7, 8. And then you see there are some features here. These are sites of unsaturation. Saturated double bonds are single bonds. Unsaturated are double and triple bonds. And so you can talk about where these double bonds are by naming the carbons where they start. So since we're at 1, 2, 3, 4, 5, 6, 9, there's a double bond at 9. We're going to call this a delta 9. You see the 9 there. So there are 18 carbons. That's what the 18 is telling you. There are 3 double bonds. That's what the 3 is telling you. And the double bonds are located at 9, 12, and 15. 9, 12, and 15 is the nomenclature. Again, we'll cover this in the fatty acid lecture and later lecture after that as well. And of course, the trade name is linolenic acid, apart from its IUPAC name or whatever. But we know from nutrition, we know that fats are important. Saturated fat, unsaturated fat, polyunsaturated, monounsaturated. And there's going to be what we call omega-3 fats and omega-6 fats. And for that, when you do the Greek lettering, you're going to start with the omega means the end. So you start at the last carbon on the fat and give it the last letter of the Greek alphabet, omega. Well, yeah. And so you say, where is the double bond? Well, you go from the first carbon here at the omega, 1, 2, 3. And so the bond is at the third carbon. So this is an omega-3 fatty acid. And we know omega-3 fats are healthy. They're healthy fats for us. But you say, wait. What is this over here? Well, 1, 2, 3, 4, 5, 6. That's an omega-6. And 1, 2, 3, 4, 5, 6. That's an omega-9. So typically we'll see this during the nutrition portion that you only call this an omega-3 fat even though it has a 6, but an omega-6 fat will not have an omega-3. An omega-6 fat starts with a double bond at position at the 6th position from the omega group. Again, we'll see that coming up later. Okay, let's take a moment to reflect and pause and take a deep breath, and we're going to do a stereochemistry review here. Stereochemistry review. And this is where we're running a little bit long. Normally the lecture should end in about 50 minutes. We've just got a couple minutes left here. But we're going to go through this because this is also pretty important. Now, you can do a very deep dive on stereochemistry, and I think the MCAT will expect you to have a good working knowledge of stereochemistry. And I pulled out my MCAT book and I looked at all the stuff they were talking about, and it's all here. So let's do this together. And we're going to talk about it from an organic chemistry point of view. We're looking at a carbon, and you'll notice that a carbon has 1, 2, 3, 4 bonds. Okay, 4 bonds, that's fine. If a carbon atom has 4 different things attached to it, 4 different, they could be atoms, they could be R groups, whatever, but if there are 4 different things, we say that that carbon has asymmetry. There is no symmetry around this carbon atom because no two things are alike. Down here, what you'll notice is this carbon atom does have symmetry because you have a CH2OH. That R group is the same as the CH2OH down here. There is a plane of symmetry, so this is a symmetric carbon. And in fact, the CH2 has 2 hydrogens. It's got a plane of symmetry. The CH2, it's got a plane of symmetry, and so forth. Okay, so no stereochemistry here at all. But up here, you've got 4 different groups. And so that's called the asymmetric, or it's called the chiral carbon. And because there's the chiral carbon, if you look at the spatial arrangement around that, there are 2 possible configurations. And it's hard to see, but the 1 can be on top, the 4 can be going down. So these 2 are together, the 4 goes down and back, and then the 3 comes out towards you, and the 2 goes away from you to the right. But over here, we've got one where the 2 comes down towards you, and over here, the 4 goes back. So this is the same, 1 carbon 4, 1 carbon 4. Here you've got 1 carbon 3 going to the right. Here you've got 1 carbon 2. No, that's not right. So these end up being mirror images of each other. They're not the same molecule. If you were to have models, and some of you may have models, you can make this and you can put those 2 molecules on top of each other. There is no way you can make them superimpose. They are different because of the arrangement of the 4 groups around that carbon. And what that's called is they are not superimposable. They are mirror images of each other. So they're called enantiomers. Enantiomer is that term. These are enantiomers right here. Now, it is possible to have non-superimposable molecules that are not mirror images of each other. They are called diastereomers. Dia just means 2, dia 2. And we'll see that coming up on a later slide here. Okay, so mirror image, non-superimposable, and enantiomers. That's the main thing here. Oh, and these links down here is a Khan Academy review that has a really nice presentation. Okay, so let's look at this mirror image and non-mirror image a bit more here. If they are mirror images, they're enantiomers. If they're not mirror images, they're diastereomers. So here are 2 molecules. Here is a mirror. And if you think about that, okay, so this carbon has a CH3 group, a chlorine, a hydrogen, and then the CH2, CH3, and ethyl group over here. And for the purposes of stereochemistry, you call this an R group. And as long as this R group is the same as that group, you just simply put an R there, and it doesn't matter about the configuration because you can move the configuration around to make it identical. So what we find is you have the stereocenter here. Hydrogen is pointing back and away. Hydrogen is pointing back and away. Chlorine is facing toward, coming out of the screen to the right. Here it's coming out of the screen. You see that these are mirror images of each other. And you're saying, wait, how do I know? Oh, so this is an R group and it's pointing sort of back, off to the right, off to the right. So these are mirror images and they are not superimposable. They are enantiomers, just like you see here before. The only difference is you've got an R group and not just a little ball. Now, an example of a diastereomer is hard to see here. This is going to be a molecule that has more than one chiral carbon. There's a couple of chiral carbons here. You can see one is here, you can see one there, one there. And in this case, you're seeing that the only thing that changes is this bromine atom is going back away from us in this configuration. Here it's coming out towards us in this configuration. There is no way that you can superimpose those two molecules where that chiral carbon would be superimposable. And in fact, there is no way that you can arrange these molecules so that they are mirror images of each other. And that's because you have the configuration of these other chiral carbons here. And we'll see that. We'll see that coming up. Usually diastereomers are going to have more than one chiral center that can have more than one configuration that prevents them from being mirror images. Okay, so that's an example of a diastereomer. All right, so what is this business of configuration? What do you showed me it's a mirror image. You said they're not superimposable. I don't understand what you're talking about. Okay, well, let's look at this carbon here. If you look at this carbon, what you'll notice is there are four groups on this carbon. Here is an aldehyde group. Here is an oxygen and OH group. Here is an ethanolic group here, and then there's a hydrogen. Okay, that's fine. So the carbon is in the middle. These dashed lines say that the aldehyde group is going back into the screen on the top. The ethanol group is going back down here. And then, of course, the OH is coming out at you on the right, and the hydrogen is coming out at you on the left. Okay, that's fine. Now let's look down here. What we've done is we've switched the two atoms. We've switched the R group hydroxyl and the R group, sorry, the hydrogen atom over here. It's down the right side, the hydroxyl on the left side. The aldehyde's still going back on the top, and the ethanol is going back on the bottom. Okay, that's fine. Now, what you have done is you have changed the fundamental positioning of these four bonds around the carbon. These are no longer superimposable. They are mirror images of each other. If you were to move this up over here, you would see it's a mirror image of the one before. And so there are two different configurations. One is called D or R, and one is called L or S. That's the nomenclature. We're going to talk about where the S and the R's and the D and L's come from now. What you will do is you're going to prioritize this. It's coming up on a couple of slides to show you how to do this, but you say, what is the atom that is connected to the carbon? What is its molecular mass? Oxygen is 16, carbon is 12, carbon is 12, hydrogen is 1. And so the smallest number has the lowest priority. The biggest number has the highest priority. Now you're saying, well, carbon and carbon, they're both 12. But then you say, well, what is the next atom that goes? Well, you have a double bonded oxygen here. You have a single bonded oxygen. Remember, two bonds. It's almost like having two oxygens. This has only one oxygen. Of course, the two 16s will win, the 116. So that gives you the priority. So you'll rearrange this thing so that the hydrogen goes back to the back. If you have models, this helps. So you just simply turn this molecule, you rotate it, going from the right around to the left. So the hydrogen is now pointing straight back. The OH is on top. That's number 16 for that oxygen atom number 16. Here is carbon, the aldehyde. Here's the carbon and the ethanol group. And you see these arrows are going in a certain way. The oxygen 16 is the biggest number. The aldehyde has two 16s on it. That's 32. Carbon is 12. That's why it's lower than the oxygen. But those two oxygens now make a 32. This oxygen makes a 16. 32 is bigger than 16. So you're going to go from priority number 1, oxygen OH, to aldehyde. So since you're going around to the right, R right means you're going around that. And so the R is actually the rectus, which means going around to the right side. And of course, the D is dextrorotary is the Latin term for that. So D and R are the same thing. Now down here, what you remember is we swap the OH and we swap the H. And if you change those two, you automatically go from what's the D to the L form. Well, how do we know that? We're going to rotate this molecule around to the right so the hydrogen is pointing backwards, and we're going to turn it so that the oxygen atom is up on top. Now, before the aldehyde was on the lower right, now the aldehyde is on the lower left. So 16 oxygen is the highest priority. Carbon, carbon 12 are second to that. But here we see the double bonded oxygen, which is 32. It is the second highest priority. Here we see a single number 16. So it's priority number 1, 2, and 3. You're going around now to the left. And since you're going to the left, it's L, but you're also sinister as left there as well. So you see how these two work together. So D or R is the same thing, and L or S. Organic chemists like R and S, biochemists like D and L. We'll see a slide about that coming up in just a minute. I'll show you this. It's okay. Okay, so what is a chiral carbon? How do we even figure this stuff out at all? We know that the different, the four groups or whatever it is going to allow that molecule to interact with light in a way that polarized light will be rotated by that. You see here, if you have plain polarized light coming into a sample, then when that light emits from the sample, it will actually have rotated the plane of polarization here. If you remember, hard light is where you cut off all the possible orientations except for one that's all aligned here. And so different chiral carbons will rotate a different amount. And that angle of rotation is the alpha. That alpha is the same. And so if you're D, you'll rotate alpha to one direction. If you're L, you'll rotate alpha to the other. Now, there is absolutely no way to know which is which. You have to measure this. There is no way to know that you're going to go to the left or the right based on D or L, whatever like that. You have to measure it. But one thing you do know is if you have a concentration of an L isomer, it's going to bend the light one alpha degree. And if you have a concentration of the other isomer, it's going to be the exact same thing. So the same concentration of an R configuration will be exactly the same bending as a 10 millimolar concentration of the L. That's an MCAT. That's MCAT all day long. And they'll ask you about that. Okay, so here's how you actually do the prioritizing. Maybe I should put this up earlier. I don't know, but you go by the atomic mass, and so sulfur has a higher atomic mass, and oxygen is higher than nitrogen. Oxygen is 16, nitrogen is 14, carbon is 12. Okay, and so when you have more than one oxygen, there's going to be more atomic mass if you have one oxygen that's double bonded or one oxygen that's single bonded versus a simple carbon here. Okay, so you always go by the first atom that's connected. The sulfur is connected to the carbon, or the oxygen is connected to the nitrogen or the carbon. So you either say it's 32, or it's 16, or it's 14, or it's 12, or it's 12, or it's 12, or it's 12. And when you get into this is how do you know which one of these 12s is going to win? Well, it depends on how many oxygens you have. If you have no oxygens, 12 is 12, and there's only a 1 stuck to it. Here, there's one oxygen, so that 12 has a 16. Here, there's a double bond, so it's like 2. So here, this carbon has 2 or 32 on it. And of course, this is like 3, whatever that is. Okay, so that's how you prioritize. So when you test your knowledge here, again, this is what we did before. I should have waited until this one here, but if you rotate this molecule so the hydrogen's in the back, if you put the oxygen up on top, because it is 16, there's 16, 12, and 12. But how do you know which one of these 12s is going to be the prioritizer? And here you have a double bonded oxygen, a single bonded oxygen. So double bond wins. You go from 1 to 2 to the left to 3 around to the right here. So since you're going around to the left, it's going to be S for sinister or L for a levorotary. And then the right is going to be just the opposite there. All right, let's test our knowledge. Let's look at a molecule that we've been looking at. Glyceraldehyde is the molecule that's on the previous slides. We've done the priorities and stuff. So we've seen the D and the L forms and how we get to that. So let's look and see if these molecules are isomers or stereoisomers or enantiomers or diastereomers. We have to look at the fundamental definitions here. So just for the sake of being very painful, let's say, are any of these carbons here chiral carbons? Because that's going to help us know whether they're stereochemistry. And you can say, yes, of course. Why would it be called D and L if it didn't have stereochemistry? But just to make sure you have this, let's look and see. So CH2OH has an R group on it, but there are 2 hydrogens on that carbon. This carbon does not have 4 different groups on it, so it is not a chiral carbon. And up here you have a carbon that is double bonded to an oxygen, and that double bond is like being bound to 2 oxygens. And so again, 2 oxygens would not be 4 different groups. There's also that plane of symmetry here, which prevents you from having stereochemistry as well. So the aldehyde carbon is not a chiral carbon. But here in the middle, what you can see is there is an aldehyde R group, there is an ethanol R group, but there's also a hydrogen atom and an OH group, and those are 4 different groups. So yes, the carbon in the middle is a chiral carbon. And what we can see between the two of them, there is a different configuration of the OH and the H. One is on the left and one is on the right. And so what we see is a molecule that has a chiral carbon. We see a molecule that has a different configuration. So are these isomers, yes or no? Well, we know that they contain the exact same atoms, and we know that they're in different configurations. And so that is the definition of an isomer. Okay, we've got that, no problem. But are they stereoisomers? The difference between a regular isomer would be no stereochemistry, but because there is a chiral carbon, because there is a different configuration in space, these things are stereoisomers. Yes, they certainly are stereoisomers. Now we get to the idea of an enantiomer. And an enantiomer is asking you, are they mirror images of each other, and are they not superimposable? Now we know by a very definition that if you have a chiral carbon and has two different configurations, because of the spatial arrangement, we know for a fact that these two things are not superimposable. So far, so good. That meets the enantiomer definition. But are they mirror images of each other? And you may be saying, well, the oxygen points up to the right, the hydrogen points off to the left, and over here that doesn't look like a mirror image to me. But remember, what you care about is the chiral carbon. And the chiral carbon says, I see an aldehyde R group. You can treat this just as a ball and call it aldehyde R. And this is just a ball, aldehyde R. And of course, they are reflecting each other. And down here, you can call this an ethanol R. And this is an ethanol R. And those little balls look like each other. So in this case, you could say, yes, they definitely are mirror images of each other. They are mirror images of each other. So in that case, you're okay. Now the question is, are they diastereomers? Okay, diastereomers. And that's going to be just the opposite. If you are an enantiomer, you can't be a diastereomer. If you are a diastereomer, you can't be an enantiomer. So in this case, diastereomers are going to be non-superimposable and non-mirror images of each other. But we've already established that this is a mirror image, and so the answer is no. These can't be diastereomers in this case. Does that make sense to you? I hope so. Okay. So what happens if you have a molecule with more than one chiral carbon? We've seen this a little bit before. We saw that one example early on about the diastereomer we saw before. If you look here, this molecule, okay, so methane is not a chiral carbon. This looks like a chiral carbon, 1, 2, 3, 4. The hydrogen's not shown, but there's a hydrogen atom on there. Of course, there's a double bonded oxygen. It does not have chirality. So this has only one single chiral carbon. What about over here? Okay, well, again, anytime you see a double bond, the answer is no. Anytime you see two hydrogens, the answer is no. But you see one chiral carbon here, 1, 2, 3, 4 groups, and another chiral carbon here, 1, 2, 3, 4 groups. Now, I've been asked before, but doesn't this have an OH and an H? And, aren't these? No, they're not the same, because the R group on this lower chiral carbon includes the OH and the H here and the aldehyde, and it is attached directly to the CH2, whereas the chiral carbon on the top is directly bound to the aldehyde group, and it has an OH2 bound to an ethanol group. So you see that these are really very different here. If you go further now, you can look for glucose and mannose and galactose. These are all 6-carbon carbohydrate molecules. And again, because of CH2, these lower carbons are not. Because of the aldehyde, the upper carbons are not. But you have 1, 2, 3, 4 carbons that do have 4 different groups. And they are all chiral. So the question is, if you have one single chiral carbon, we've seen that there are 2, the D and the L, or the R and the S. So how many configurations would you have if you had 2 chiral carbons? Well, D and S, or D and S, that would be, 2 times 2 would be 4. So 2 chiral carbons, 4 total configurations. And what it comes down to is pretty simple. If you have n stereocenters, you have 2 to the n possible stereoisomers. So 1, 2, 3, 4. So 2 to the 4, you'd have to hold up 2 2s. That would be 2 times 2 is 4, times 2 is 8, times 2 is 16. So for 4 chiral carbons, there are 16 configurations. And you see how things complicated really, really quickly. And that's why molecules with more than one chiral center can oftentimes are called diastereomers. So let's look at that a little bit more here. So just reviewing the terms, we have isomer, stereoisomer, enantiomer, diastereomer. We saw that in the example before, but now we're going to bring in a thing called an epimer. An epimer is going to be stereoisomers that differ in the arrangement of only one only one of several asymmetric carbon atoms present here. So like those carbohydrate molecules we're going to see coming up in the next slide, we're going to see that only one of those carbocarbons will be different. Let's take a look at it and see. Let's compare these three molecules here on the left. We have D-glucose, D-mannose, and D-galactose. You don't have to memorize that. Even in the carbohydrate lecture, you don't have to memorize that. And we see that there are 4 chiral carbons. We've established that already. If you start comparing and say, well, this carbon here looks like it is reversed between glucose and mannose. Okay, that's different. But it looks like this carbon's the same. The OH is on the left and the H is on the right. Here the OH is on the right. So it looks like glucose and mannose differ only in this second carbon. Wait, why do you call that the second carbon? Because the most oxidized carbon is the aldehyde group. So that's carbon number 1, 2, 3, 4, 5, and 6. The CH2OH is the 6th. Now let's go all the way over here to galactose. The second carbon on galactose looks just like the second carbon on glucose. But the second carbon on galactose is different than the second carbon on mannose, okay? But you see galactose and mannose, the same on the third carbon, different on the fourth carbon, same on the fifth carbon. So you can do those comparisons and stuff. So let's test our knowledge based on what we see here. Which one of these molecules are stereoisomers, which are enantiomers, which are diastereomers, and which are epimers? Now, this is going to be a lot harder, and I don't believe that the MCAT exam would ask you anything this hard. They might, but they tend to stick to single carbons with asymmetric carbons with different groups. They tend to go with that. But just in case they go into the more biochemical range, let's do that together. So what do you think? What do you think the answer is going to be? Okay, so let's start with the first one. Oh, sorry, all the answers popped up. I forgot we didn't do the 1, 2, 3, 4. So which one of these are stereoisomers? All of them are stereoisomers. Okay, yeah, they all have the same number of carbon atoms, the same number of oxygens, the same number of hydrogens. They're just configured differently. So they are all, and they have chiral carbons in there. Are any of them enantiomers? Are any of them non-superimposable, but mirror images of each other? Now you say, don't you treat this as an R group and an R group and an R group and R? Yeah, okay. But the R groups themselves are different because the chiral carbons are changing configuration. If you call this an R group, the lower part from carbon number 2 down, that R group is different than the other 2 R groups. And so those R groups are not the same. They're not mirror images of each other. Or you could focus on carbon number 1, 2, 3, 4, and you could say the R group above, well, you're saying that these are not the same R groups, okay? It is at top, but it isn't at the bottom. And so since the R groups are not the same, then you can say they are not enantiomers. But because they are stereoisomers of each other and they're not mirror images, they are going to be diastereomers. They're going to be diastereomers because they're not mirror images. Now, which one are epimers? An epimer is defined as being sorry, I need to advance this. That's why they're all stereoisomers. You see, they all differ from each other in configuration. None of them are mirror images of each other, so they're not enantiomers. All of them are diastereomers because they are stereoisomers, but they are not mirror images. And then when we look at epimers, we're saying which ones are going to be different in only one position here. And if you look, then 1 and 2 are different, carbon number 2, but all the other carbons are the same. See that? So only carbon number 2 is different. That's 1 out of all the others. And so 1 and 2 are epimers. And then if you look over here, you can see 1 and 3 are epimers. They differ only at position number 4. 1, 2, 3, 4. Everybody else is the same. But mannose and galactose, they are not related at all because they have more than one. You see there are a couple places that are changed. Like for example, carbon number 4 and carbon number 2. So more than one position is changed here. So that's why mannose and galactose are not considered epimers. So we're going to take a quick look ahead here. We're going to see that amino acids, by nature of their molecule, have 4 different groups on them. Usually there's an R group over here. Sorry, R group down here. There's always a hydrogen, there's always a carboxyl group and stuff. And so we're going to see D and L configurations of amino acids, and we'll develop the carbohydrate a little bit more when we get into the carbohydrate lecture. So I know this ran a little bit long, but it's a pretty good fundamental treatment of the material that we have. So hopefully this will be helpful. If you have any questions, please let me know by email, or we'll have Zoom help sessions or whatever. We can talk about this some more. But apart from that, I'll say thank you, and thank you for giving me an extra 21 minutes on this lecture. I really do appreciate it.